So question number 1 says, how many radians are on 365-degree circle or degrees? Now remember, I've been using this paper plate, and when we're talking about radians, we're talking about this side of the paper plate. And in a full circle, there's not only 3.14, but there's a total of 6.28 rad is the correct SI unit. But for question number 2 says that this object rotated 16 times. And out of the 16 rotations, how many pi rads? Oh, look at the same paper plate I've been using this whole 2 weeks or so. When I turn it over, this is what I wrote on this side. A half a circle is 1 pi rad. The other half is another pi rad. So if you rotated 16 times, 16 times 2, because there's 2 pi rads in one circle, equals 32. Hold up. The correct unit is a pi rad. That is a unit. That is a unit. So I wanted to go over the answers with you today. I will post a blank quiz with the answer key on D2L after class is over today. The next part of the question, we have a lab next week. Now with our lab, we have some free body diagrams to do. And we have a test, and we have a semester exam. So let's take a look at the questions here. This question over here asks you, hey, draw a free body diagram of a soccer ball. Now, I don't know if the soccer ball was kicked by somebody's foot or if the soccer ball was in the middle of the grass and the wind pushed it. All I know is that it is rolling in the grass. I am not going to take points off of this, but I want to go over. When you draw this for the semester exam, for the test, you are not to draw the grass. You are not to draw somebody's foot showing that they kicked the soccer ball, because I don't know if they kicked it, okay? All you are to do is draw the soccer ball or draw a little box, okay? But here you go. I'm going to just draw that soccer ball. That's it. I'm not drawing anything else. Now, look, it does say label the correct forces. So for that situation, you do need to label the F's. You do not need to add any number value because I don't know those. Now, the fact that it is moving to the left means that the left arrow should be the biggest arrow, or FA. Again, I don't know if that applied force came from somebody's foot or if it came from the wind. I don't know, okay? FF in our notes all says that it's always opposite to the applied force. And I don't care if you're on Earth or if you're on the moon. You are going to have an FG or an FW, which we call weight force or gravitational force. Call it whatever you want. But whether you're on the moon or whether you're on Earth, you're going to have a gravity force that pulls down towards the center. But because it's on the grass is the normal force, Fn, that is opposite to gravity. Now, the other thing that I want to make sure that I am explaining is that the gravity and the normal force should be, I shouldn't have to use a ruler. They should be equal in size or equal in magnitude, okay? So let's go ahead and move on to the next one. Tells me that this rock is sliding downward. Now, I can see that it's at an angle or it's on some type of surface. I don't know if it's a mountain or if it's a sidewalk, but it's at an angle. And since it's sliding downwards, then the biggest arrow should be FA. Again, I do not know if it's because somebody kicked it or if it's because the wind blew it down. My notes tell me that frictional force is opposite to the applied force. And I know that gravity or weight force, no matter the orientation of my object, will always be pulling straight downward. But in my notes, I said it before, and this is where we may lose points, but I guarantee you on the test, quiz, semester exam, we will lose points if your normal force is not perpendicular to the surface. I know I said it before, I'm going to say it again. If this is my surface and it's at an angle, then my normal force should also be perpendicular to the surface. And if this right here at the end of the arrow was to touch the surface, it should be able to form a 90-degree angle, okay? So, but for an example, if this is on a flat grass, I'm going to assume, I don't know if it's at an angle, then this right here, the normal force can form a 90-degree angle, perpendicular to the surface. This as well. So make sure, because I know that our lab next week or so is going to have something at an angle. I just want to make sure I went over that. Then this one, on the answer key. On the answer key, when I did this quiz last night, I left this part blank. I'm not going to grade anyone's quiz, but that's because what if you had a question? Miss Munson, is the car coming to a stop at the red light, like it's slowing down and pushing on the brakes? Or Miss Munson, was the car already stopped, like it broke down and it's not moving? So I want to make sure that I tell you on the test or semester exam, when you see this question, guarantee again, the car will already be at a stop and it's not slowing down. Meaning my object is not going to have a right and left arrow, which is okay. We don't always have to have 4 arrows. Sometimes we can just have 2 arrows. And so I wanted to make sure I went over that today. I will not count anyone against that. FW or FG and FN. And again, my FG and FN are going to be equal size if my object's not bouncing up and down. Okay? The next one, for those of us who are in pre-cal or will be taking pre-cal, I want to remind you that that fraction, 11 pi over 6, is actually a radian or a rad in pre-cal. Now, your calculators are pretty awesome. So if you typed it in, sometimes it will give you in a pre-cal format. That is okay. But to convert this out of a rad into a degree, remember I had mentioned, hey, here's your formula chart. But this equation is a memorized. All of the professors that I know here at COM make you or have you memorize. I have this equation sideways. If you turned this sideways, here it is over here. You didn't have to memorize it. I said it before I left out of town. I'm telling you again. I feel like you have a lot to memorize. This one wasn't one of them, okay? So in this situation, if we want to convert from rad to degrees, you're going to multiply it by 180 over pi. My pi's cancel out mathematically. You go ahead and do the math. It comes out to 330 degrees. Then you had your protractor. You went ahead and you know that all circles start off at 0 degrees and rotate in the positive direction. And look at this. There is not a negative, so this must be positive, meaning that you're going to rotate that direction. 330 degrees is about over here. Okay, when you got your protractor, it's about in that section or that quadrant. Alrighty, so I'm going to keep going. This is another free body diagram, but for this free body diagram, It actually gives you the magnitude. You needed to identify which type of force it is. So looking at this, my normal force is 2 newtons. My applied force, which is going to be 5 newtons. My weight force, which is the same thing as gravitational force, is going to be 5 newtons. My frictional force, which is opposite to my applied force, is 3 newtons. But over here, they ask you to find the net horizontal and the net vertical. So because horizontally, my arrows are opposite and vertically, my arrows are opposite, I'm going to subtract. For this situation, it would be 2 newtons and 3 newtons. Then the next question here, it was pretty easy cheesy. It literally says to draw the overall net direction. Like when I look at these two answers right here, because they're not zeroed out, this one horizontally, the bigger number is moving to the right, and vertically, the biggest number is moving down. So for this situation, all you had to draw was an arrow in this quadrant. That was it. That was it. Now, I actually thought number 6 was kind of a difficult equation. It was a 3-step problem, okay? It was having you think. Now, step number 1, hopefully you recognized that this number is in pounds and it needs to be converted. I need to convert 112 pounds into kilograms by dividing it by 2.2. Hopefully you did that and you got a number of 50.91 kilograms. Now that's not my answer, but I have to. I cannot use pounds in any math equations for physics. We must, remember those 7 parent units I told you about in the beginning of the school year? It must be in kilograms. It can't even be in grams. Even grams wouldn't work mathematically. Now, they told me that my object is traveling at a velocity of 5 meters per second, and they would like to know the magnitude of the force. What is the force required to bring this object to a stop? VF is 0. That means that this must be a VI. And it took 8 seconds T for it to come to a stop. Well, my equation that I needed was F equals MA. I have the M now, but step 2 was to calculate the acceleration, and we used our old school kinematic equations. VF minus VI over T, or 0 take away 5 over 8 comes out to, yes, a negative 0.625 meters per second square. But that negative only means it's slowing down. We do not need that negative in my answer. So if you did, I'm not taking off because I'm explaining it, that we are calculating the mass of 50.91 multiplied by the acceleration of 0.625, and your force is 31.82 newtons. If you wrote a negative, I'm not taking off, but I am explaining it so in the future you know to not add a negative with it, okay? The next question, again, like I said earlier today here on question number 1, when you read the question, it's going to either ask you for radians or pi radians, okay? So in a half a circle, 3.14 rad, in a full circle, 6.28 rad. In a half a circle, there are 1 pi rad, and in a full circle, there are 2 pi rad. Okay? Then the next question says, well, if you rotate 10 times, how many pi rads are in 10 rotations? Or 10 times 2 equals 20 pi rad. There you go. The next question, though, asks you for radians. Remember, this side is the pi rad, this side is the radians. So for this one, if you rotate it 6.2 times, you can do either multiply by 2 pi, or you can do 6.2 times 6.28. Either way, you're going to get the same answer of 38.94, depending on how you rounded on that pi rad. Okay? Then, question number 11. On number 11, they actually, again, we were back to these two equations over here that were sideways. They gave you the radian, and then they gave you 3 different degrees. Now, when you type this into your calculator, your answer over here, for me, I prefer it to be a decimal, but you may have on your calculator, may have came out looking like a pre-cal fraction. That is okay. But the fact that all of those are rotating in the negative direction is important. So I wanted to make sure I went over that today verbally. So because we are moving, remember, negative direction, then negative is important. To solve for this, I had to multiply 180 over pi. And for all of those, you had to multiply pi over 180. Okay? Now, in that situation, we can cancel out the pi's, but you do end up with a negative answer. Negative 30 degrees. Look at that, negative 30. So if you wrote the same answer, you're completely good, but it should be a negative, either pi over 6 or a negative 0.523 rad. Okay? Again, over here, you multiplied pi over 180, but your answer is going to be a negative, or you could write it out in the format on your calculator, may have gave you 7 pi over 6. If you multiply and divide this out, it comes out to the same number. Okay? This is just pre-cal. This is physics. Okay? That's the only difference between that. Over here, negative 2.79 rad or negative 8 pi over 9. Either way, again, they are the same thing. Okay? And then after that, I think there was one more page. This one was easy. Remember, we always start off at 0 degrees over here on the right. They asked you to draw the positive rotation, so your arrow should have looked something like that. But a negative rotation, your arrow should look something like that. Again, positive, you start at 0, you go up. Negative, you start at 0 and you go down. Then on number 13, I needed to pull out my protractor. I didn't have it with me. So for this situation, I'll answer this after class. I'll post the answer on D2L. But 78 degrees, not only is it 78, but it's negative. Remember, we always start off at 0 degrees. And if you're going to rotate negative, then you're going to start down, and that's how you're going to rotate. Your theta should come somewhere over here to this direction. Why? Because you rotated in the negative direction. So I just wanted to go over these with you verbally so that way you'll have that. Alrighty, let me go ahead and move this out of the way. Before you leave today, I have extras over here if you want to pick one up to practice. but I will post this and I will post a blank quiz on D2L today, okay? Other than that, we're at notes. So we're going to stop when we get to torque. Then after that, we have notes tomorrow. If you have something going on, I understand. I'm going to video it like I try to as much as possible. I know some classes, some schools have PSAT testing going on Halloween, so just in case. All righty. Here's where we ended up with our notes at centripetal acceleration. Now, on centripetal acceleration, we actually wrote in those words over here before we left. So let me go back to find those words again. Those words say that, is the object moving in a perfect circle accelerating? And the answer is yes, it is. But that's because that we know that objects that move in a circle not only involve the speed, or what we call magnitude, it also involves the direction as well. And because it involves a direction, then that means that it's a vector quantity, and any object moving in a circle is always moving constantly and constantly changing its direction. So its direction is constantly changing. So the object, it says here, is, yes, accelerating. This is what we call centripetal acceleration. Centripetal acceleration's definition is the acceleration of an object moving in a circle. Again, for any object to move in a circle, it has to continuously change its direction. It can be maintaining the constant speed, but yes, it still is accelerating. Okay? So we wrote down our equation. Yes, this equation is on the formula chart, which is great. Then we have a couple of practice problems. It says here that Bob is running around a perfect circle track. Now, the radius of this track is 2 meters, and the tangent velocity is 5 meters per second. What is Bob's acceleration? Now, I will tell you that these are easy, cheesy questions, and on the quiz and test, you're going to have to first calculate the tangent velocity. After you do that, then you can calculate the centripetal acceleration. So for this situation, we have AC equals VT squared, don't forget to square that, divided by R, or 5 squared over 2. 5 times 5 is 25 divided by 2, which comes out to 12.5 meters per second square. Or, even though you're moving in a circle or a straight line, you still have the same units, which is meters per second square. The next question, though, they try to trick you because they told me that Sarah has this bike that she's riding in a circular path, but they told me the diameter is 50 meters. We do not use diameter, we use a radius. So the radius is 25. That is the number I need. Do not let them throw you off. It also told me that her speed is 10 meters per second, or tangent velocity. Remember, tangent velocity, tangent speed, or the other words that we use was angular speed. It's the same thing, tomato, tomato. How fast is it moving? Now, centripetal acceleration is the tangent velocity or tangent speed squared over r, or for this situation, it would be 10 squared over 25, not diameter. 100 divided by 25 is 4 meters per second square. So again, I think those are pretty easy cheesy. But the next one, I'm going to go ahead and give you the equation here. And I'm going to go ahead and get my highlighter out. Remember, I like to highlight questions or formulas that are not on the formula chart. But this is kind of on the formula chart. So I'm just going to come over here and I'm actually going to star it. I'm not going to highlight the whole thing because the equation is FC equals MA sub C. And on the formula chart, F equals MA, like that, is on the formula chart. Yes. FC equals MA is not. So I don't want us to get to the point where, oh my God, I can't do this. You can. Right here, force equals mass times acceleration. This equation is on the formula chart, except it just doesn't have the little c's. So it kind of is, kind of isn't on the formula chart. I just wanted to make sure I went over that with everyone. The FC is centripetal force, and we know that force has a unit of a Newton. Same thing here, even though you're moving in a circle. M stands for mass, and we cannot use grams, we cannot use pounds, it must be kilograms. AC is centripetal acceleration, which is meters per second square, okay? Centripetal acceleration or meters per second square. Centripetal force, it says here, is that net force required to keep an object moving in a circle or a circular path. Okay. How much force is needed to keep it in a circle? So, I think last week or whenever it was, I had this, or earlier this week on Tuesday, this little charger over here. It's connected to this wire, which is perfectly fine. Now, when I rotate this little charger on this wire, if I don't hold on to it, last time, earlier this week on Tuesday, I said, if I don't hold on to it, it's going to fling and fly off. It will just fly off if I let go. The centripetal force is how much force is needed from the wire and my hand to hold it, so the moment I let go, whoo, that sucker's gonna fly off. Not only fly off, but we can calculate that fly off. That was our math equation earlier this week. That's called tangent velocity. Not only that, but we talked about when it flies off in a straight line, we call that the tangent line, right? So the centripetal force is going to be some type of tension, which was a perfect example. I had that rope or that wire, that tension force that held it so it doesn't fly off. It can be a friction, no force. For an example, let's say you're driving to school and all of a sudden there's a dog or something jumps out in front of you. You have to swerve your wheel, and when you do that turn, thank goodness you got good traction and it's not a wet, rainy day. So that way the friction keeps you on the path of the road. If not, you would fly off into the curve or into the ditch. Or some type of gravitational, which kind of doesn't make sense. Let's talk about that. A gravitational force. Now, centripetal force holds it in to the center of the circle. That makes sense. Tension, my wire's holding that little box. so it doesn't fly off. That makes sense, Miss Munson. Oh, when I'm driving on the road, my tires in this road need to have some type of friction, so that way when I turn really fast, I don't just fly off into the ditch. But what about gravitational force? Okay.
Like the sun and the solar system?
Okay. What about you here on Earth? Gravitational force is keeping you on the ground. Gravitational force is actually a center towards the center, right? Because even though we live here at the top of quote unquote planet Earth, those penguins, or what about the people that live like in South America, right? They're not falling off of the Earth because everything, gravity pulls towards the center, and gravitational force keeps you in the center of the circle so you don't fly off, which makes sense. So centripetal force is always acting towards the center to keep the object in the circle. Thank goodness for gravity, because it keeps us on Earth. It keeps us here on Earth. We've got a couple more equations for today, and then tomorrow we'll finish our notes, and then I will post whatever blanks that we're missing on D2L for you. So we just wrote down this equation. Let's go ahead and practice. And again, remember, on our notes, they're kind of easy cheesy. On the quiz, we're going to take it up a notch. Haley, it says here, is in a car. His car has a mass of 155 kilograms. If it was in pounds, you must convert. Now, they gave you the centripetal acceleration, but what if you have to figure out the tangent velocity? From tangent velocity, you have to calculate the centripetal acceleration, and from centripetal acceleration, you now have to calculate centripetal force. That is what you're going to have to do come quiz and test day. Now, centripetal force, remember, is on the formula chart, but it looks like this. F equals ma. Or 155 multiplied by 2 equals 310 newtons. Easy cheesy. All right. But on quiz and test day, you need to be ready to calculate centripetal or tangent velocity. From tangent velocity, calculate centripetal acceleration. And from this number, then calculate centripetal force. All right. Now, let's come over here to this next word. Remember when we talked about positive and negative rotation? And if this is a circle, we always start off at 0. We rotate up or counterclockwise for positive. We rotate down or clockwise for negative. Now let's talk about the words centripetal and centrifugal. Those words are a couple more words talking about circles. Now, centripetal, we actually already talked about already. Centrifugal is a different word. We haven't talked about that yet. Now, I talked about centripetal already a few times. For an example, on the previous page, centripetal force is always acting towards the center. So the word centripetal force, centripetal acceleration, centripetal velocity, centripetal speed, I don't care. But as long as it has the word centripetal in front of that, that means that it's always going to move towards the center of the circle. Or we call that in physics center seeking. It moves towards the center. But the word centrifugal is a new word. Centrifugal actually means the opposite. It means that it moves away from the center, or we call that center fleeing. It flees away. It moves out, away from the center. Now, let me explain this next part before I actually fill in all the words. So what they're trying to say here in all of these words is that, for an example, back to my little box over here on this piece of wire. If I rotate this box on the wire, we talked about it already. If I was to let it go, or if it was to break loose, it would fly straight out in a straight line, and we call that tangent velocity. Now, because of the wire, and because of my hand holding it, it stays moving in a circle. We call that centripetal force that's holding it in a circle. But truly, the moment that my hand moves away and I lose grip, it flies out. That flying out is actually centrifugal. Centrifugal force actually is what occurs all of the time. Centrifugal force is always in existence. Who actually came up, or who said that? That was actually Newton and his first law of inertia. His first law of inertia is 100% correct, even with objects moving in a circle. Objects moving in a circle, they always have some type of sensation of an outward lean or pull. Have you ever been in a car? Have you ever seen like those Jeeps without a door? Oh my God, what if they were to lose traction? What if they did not have a seatbelt on and the car goes crazy? You're gonna fly out. That outward sensation of you're gonna fall out of the car is called the centrifugal, which is actually always in existence. Who said that? Newton, his first law of inertia. But because we have centripetal force, because we have seat belts, because we have doors on your cars to help hold you in, that is going to be that inward net force which is going to be the centripetal force. And that centripetal force required to hold you in that circle. Because truly, if that was missing, you would not move in a circle. You would fly out in a tangent straight line. It says here that there is that inward direction that is this invisible force or acceleration, which a seatbelt, the door on the car, all of those are examples that hold you inward. Because without that inward force, you would move in a straight line, tangent to the perimeter of that circle, right? We called it last week or on Tuesday, the tangent line. And without this inward centripetal force, then you would fly in a straight line out. But Newton's law says that all objects want to move in a straight line. That's their true nature. Their true nature is to move in a straight line. It says here, when making a left-hand turn in a car, your tendency to be thrown right across the seat or to hit the side of the door was not due to some type of unnatural or natural force. It's actually the natural straight line of inertia that makes you want to move in a perfectly straight line. But that's Newton's first law of motion. That actually is what's happening. But we have the seat belts and friction and tension force and maybe that door on your car that helps keep you inside so that way you're not moving out and you're not going to keep going in a straight line, flying straight out. Instead, we have an inward centripetal push that keeps you inside of the car and you don't fly out. So what's it all come down to? Truly, Newton's first law of inertia will naturally take over. We call that centrifugal. That is what truly happens. But because of friction, gravity, the seat belt, we actually have a centripetal force that actually holds us and keep us in the circle. This is unnatural. This is what naturally takes place, okay? After that, I'm going to fill this in later on. I just want to simplify all of those words into simple. So here we go. This is what I told all the students, and this is how I explain it. The word torque, I'm not sure if you heard that before. Maybe you've heard it before when dealing with wrenches. You know, you can buy different size wrenches with different handle length. You can buy smaller ones, you can buy super large wrenches. Now, the larger the wrench, the easier the force needed from you to do the work on whatever machine you want to. But let me give you an example without having to use tools, okay? I have 3 boys, and out of my 3 boys, I will stand by a door and I will not open the door at all. I expect my sons to make sure that they open a door for any lady, any woman that they see, or any old person. That's the other thing. It could be a super old person. Open the door for them. But I'll stand in front of the door. I won't even say one word. And they know by now, they're old enough that they better open the door for mama. But if I'm standing right here in the way, and one of my kids has to come over here to open the door for me, would it be easier for them to open the door here by the hinges? Or would it be easier for one of my kids to open the door further from the hinges? Further from the hinges. That's what we call torque. So in physics, we say torque has an equation, and the equation is force, because didn't I have to use a force to open that door? Force times, we say radius, but actually it could be distance. The hinges on this door, if this part of the wall was missing, the door, imagine the door moving in a perfect circle. And the further from the hinges that we move out from the circle, the less, look at that, the less force needed to open the door. But if I put my hand closer to the quote unquote hinges or the radius, then it takes more force out of me to make this torque or this turn occur. So that's what torque is. To simplify it, torque has an SI unit of a Newton meter. They don't cancel out. Radius or distance is going to be in meters. And capital F, which you already know stands for force, right? That push, which is in newtons. That's where we stopped today. Believe it or not,